Okay, welcome back to the channel. This is the Prokon Geek, and we will be looking at load takedowns now, as this is what will help us to proceed to the analysis and design of our building in Prokon. So yes, you've been waiting for it. We've been doing layouts, and now we're actually doing the takedowns, which will help us analyze and design the building. So the reason why takedowns are very important is it's simple. You cannot design if you don't know the loads and the setup of your building. So this is why it was important for us to do the layouts first, because the layouts and the load takedowns help us identify the load, particularly the one that is going to the foundation, which is the first place where we start when we are designing or analyzing our building. Yes, so this is what happens when we're calculating loads. We start from the top, but when we're analyzing and designing, we start from the bottom. So before we begin, you need to understand the load transfer. That is the basic load transfer that happens in frame structures or buildings in general. How do loads interact or work when they're in buildings? So what we need to understand, to illustrate this, we will just use a flat roof frame structure or building. So essentially what happens is this flat roofed frame structure will have a flat slab at the top. So what happens is you have your loads which are applied on the roof, obviously by rain, snow, or whatever is on the roof, right? So they move from the roof slab, they go onto the eaves beams, and then from the eaves beams they go onto the columns which support these eaves beams, and then that load is then transferred from these columns all the way to the columns below that. But before we even go to the foundation, at the slabs which are below the roof slab, will also have some load which will be on them. So that load is then taken to the slab, and the slab then distributes it to the beams which are monolithic with it. Remember, the beams are cast as L or T flanged beams which are monolithic with the structure, and these beams then transfer the load to the columns which are also below the columns that are coming from the eaves beam. Yes, it's a bit of a tongue twister, but that is what happens. So that is basics of load transfer in framed buildings or in buildings in general. So now that you have an idea, the next thing we want to see is how do you actually do this takedown given a structural layout, a drawing from an architect, or anything that you need. So before we proceed, you need two things. Some form of a program. It can be Excel, right, or MathCAD. You already saw my MathCAD sheets that I had. So you need a program such as Excel or MathCAD to do the calculations, and also you are going to need a shell. By what I mean is a shell is any shell that will represent your structure, which you will make from your layouts, which are what we have already done. We did our layouts, ground, first, eaves, and now we came up with the shell. And so I think the best thing to understand the shell, let me show you how essentially it's easy, but let me just take you through what this shell is and how you essentially come up with it and how you analyze this to do your takedowns. Alright, so essentially looking at the shells, how did we come up with the shells? So unfortunately I'm using my old PC, so I'm using AutoCAD 2007, and there's some glitches in there. But essentially when you're coming up with a shell, you need to analyze the section of your buildings. Okay, the shells for the different levels. So in our case, we're gonna have two shells, one for the roof level and then one for the first floor level. And the reason we are not going to be having a shell for the ground floor level is because we do not have any slab or ground beams which are feeding their loads into our columns, which will then feed to what we call the bases of our foundations. So basically with this ground slabs, these are just feeding directly to the ground. The ground is good for them to just feed to there. It's normal, it's like in a normal house, and as you know, normal houses, we do not even design the ground floor slab. It's just throwing in a 150mm thick slab with S193 mesh if it's going to be normal use, and 290 something if it's going to be a garage, it's going to be a gym, but in this case we're just going to be a classroom at the bottom. So simple design. So what we needed are two shells, one for the roof level and then one for the first floor. So to do that, all we have to do is window which drawing again, tutorial layouts using AutoCAD 2007, man. Woo! some glitches using my old machine. I don't have electricity, so yo, this is what it is. Now, so as we see, we have the roof floor level shell, which is essentially at your roof level. You just have you have this eaves beam, and this whole area is going to be covered by the roof. So that area covered by the roof, we represented it this way. And then when it comes to the first floor level, you're going to have the slab which is going to be the gym, or let's just call it the classroom but we just given allowance for it to be turned into a gym, you never know. And then you're obviously going to have the balcony, and these circles represent the columns, and I've color coded them, and we're going to talk about the color codes later on. So once you have your shells, to just do your shells, it's easy. For example, let me just represent this shell. What you just did is just create your line. It's going to be 6,000, and then you're going to go do another 2,000. Then obviously you're going to go 20,000, and then 8,000. And then you're going to close off the drawing, and then you're going to offset these lines by 5,000. Just make sure we good. 5,000, 5,000, 5,000, because we are following the setup that we have on our structural layouts. 5,000, 5,000. Then obviously you want to make this blue so that they represent the shell. All right, so this is what I did. I just made them the same line. Then you want to create a line which is obviously for the balcony. So we're creating the first floor level shell, how I created it. So once I had this shell, as you can see right now on the drawing, the next thing that I had to do was to create the distribution areas, or the tributary areas. So as you can see, each column or each section transfers its load differently. So for the first floor, this portion that I've highlighted transfers its load to this orange column. Then as you can see, this portion which does not have a highlight transfers its column to this column which I have clicked right now, and this column also receives a portion of the load from the slab, which from this section where my cursor is dancing at right now. So essentially that's this one. Let's just hatch it so that you can see. Right, I think that hatch is okay. Pick points. Let's pick points. So for this column, all right, okay, this is just two. This is different from AutoCAD 20. All right, okay, that is, dude, how did people use 2007 back in the day? This is funny. All right, it's playing, it's music, we're going. Okay, it's taking too long. This hatch, and this PC does not have as good as a processing power to handle this thing. All right, so essentially we are done now. So this column, as you can see, the area that I've shaded in green transfers all its loads to that portion of the beam and to that column. So all the loads from the slab and the beam in that portion are transferred to the column where, okay, as you can see, it's now dancing a lot, it's taking too long, but it transfers all its loads to that column. Right, so that is how you do, that is what essentially what we mean by a tributary area. So the gist of it is to calculate now the loads that are coming from this roof eaves beam going to this column, and then you calculate the loads which are going from this slab to the columns using each column's respective tributary area, and you also do it for the balcony, and then you proceed. And to do that, now this is where you need Excel, where you have a calculator which helps you to calculate these loads, and this is what we are now doing. Alright, so to save time, we're just going to be doing the load takedowns for one column or one section of this building, and the rest of this you can do this on your own, or we can do it on another separate series if you want me to do so. So to save time, I just nominated the worst case scenario, which is code red. So the column which is in red, as you can see, and this is its tributary area at the first floor level, and its tributary area at the roof level is as shown. So the columns in red. So essentially these are middle columns when you really look at them, when you look at them at the first floor level. At the roof level, the external columns, but we're just going to do it as a middle column when we look at it from from what you call this, from the first floor level. So to do that, yes, let's go to my folder where I keep my sheets, and we're gonna go to the middle column takedowns. So let's just wait for it to start up, and there we go. So the first thing we want to do is, we said you do your loads starting from the roof going all the way down. So let's open the roof section. So essentially with this sheet, I created it on my own. I enter wherever it's blue, where it's green it's automatic, where it's orange it's from a code. So let's start. So for the roof, provide dimensions of the tributary area. So what we have to do is go to AutoCAD. So we are at roof level, so it's 5.625 multiplied by 3. So it's going to be 5.625, and then it's going to be multiplied by 3. Then the same time we need to provide the roof, the pitch of the roof. In our case, the roof is 30 degrees, so that there's a reduction factor. So this is the area it calculated for us, 16.875 square meters. Then the dead load factor is 1. I got this from the American structural concrete whatever code, because SABS and BS did not have this. And the calculated load is 19.48557, which is coming from the roof for that section, which is cool. And then the next thing is the live load from the roof as well. So this one has a factor, it's also automatically calculated. The factor is 2 kilonewtons per square meter, and this is the live load coming to that column from that roof and going all the way to the foundation. And the next thing we want to take care of is the slab. So for the slab, now we need provide dimensions of tributary area. So we go back to AutoCAD, and then we see first floor level, and now the dimensions are 5625 multiplied by 5. So that is okay. What you have to do is 5.625, and then this is 5 slab thickness. We put it at 200, 0.2 meters, and the screed thickness we're gonna assume 0.50 centimeter screed, so 0.050, and that is good. So the area is that. Gamma, this is the unit weight of the concrete. So from SABS or wherever you look at, even if you look at Greg Parrott, it's 24. So code of practice or location is BS/SABS. So 24 plus that, and then you calculate the total load coming from the slabs, which is 168.75. Then now we need to look at the live load from the slab. All the input data is the same as above. So now the only thing we need to enter here is the factor that we're going to be using. So I am inclined to use 5, because this area may be changed into a gymnasium or anything, so we're not too sure what it's going to be. So we're just going to put 5, because normally you're supposed to take 3 from section. I'll put up the code for you so that you can see where you're supposed to take 3 and where you're supposed to take 5, but we're going to be using 5. So let's just key in 5, and we get 140.625, because Africans tend to put different uses to the building. So we don't want our building designed as a classroom to be later on used as a gym or as a church, and then it falls like it did in Nigeria. We don't want that. So the next thing that we're gonna do is load bearing walls or slabs. So in this portion, let's see, do we have any walls on the slab? No, the walls are not on the slab, because the slab is this area where my cursor is dancing, but the walls will essentially be on the beam. Yes, if you look at your layouts when it comes to the first floor, let me just remove this. Your loads are going to be on the beams and not on the, because the beams are part of the slab. It's their flanged beams, so we are going to put those walls on the beams and not on the slab. So we don't have any walls where my cursors are dancing, so we are good to go. So in this case, walls on beams, do we have any length of walls? It's 0. Do we have any height? It's 0. Unit weight of the bricks is 23. Default wall 230. We don't have a 230 wall, so the load from the walls on slabs is 0. Then the next thing we want to do is calculate for the beams. Now for the beams, the beam depth, I entered it as 300, but since it's going to be an L or a T beam, 200 is going to be supplied by, what do you call this? The slab, and then 100 is going to be the effective depth that is only coming from the beams. So you would put 0.1, but then also we need to remember we're going to have eaves beams, which are going to be 0.2. So this essentially becomes at most 0.2. I might put them at what do you call this, 0.15, but at most there will be 0.2. so the effective depth of all our beams still remains as 0.3. then the beam width at the most it's 0.3230. thus the area of the beams is 0.0690, which is okay. Then the length of these beams, okay, the length of these beams, which are our beams, let's see, go back to AutoCAD, let's go back to our shell. So these are the beams which are going to be contributing to this. We're going to have this portion where it's just but bounded by the shaded area, so there's going to be 5625. then we're also going to have this portion bounded by the shaded area as well. It's going to be 5 meters. So what you're going to do is 5.625, and then you're gonna have 5 meters to give us a total length of 10.625. and then gamma, the unit weight for concrete, is 24 multiplied by the length multiplied by the square area. Then you get the load, which is going to come from the beams, which is, it's not even too much. And then you're going to have the load bearing walls on these beams. So the load bearing walls on these beams is essentially, let's no wait let's not say it's essentially, let's see what. So I think we're only going to have walls on this section. Yes, as you can confirm from your layout, you're only going to have walls on this section of the beams, so which the length of these beams which are contributing to that column is going to be from there to there, which is essentially 5625. so you go back to your calculator, then you enter 5.625. then the height of these walls, the maximum height will be 3 give or take, 2.8 to 3 give or take, if you look at our structure. So we're just gonna put them at 3, so it's gonna be 3 meters, so that's okay. So the load which is be distributed to the floors from the beams or to the foundation is going to be 89.626875. Then the next thing, you're going to be looking at the columns. So for the columns, you can change, I personally can choose whether it's a circular column or it's a rectangular column, and as you can see, it's changing whether I do it's a rectangle or circular. So since we have rectangular columns, section depth, the depth is definitely, I entered 300, I remember, and then the width was 0.230. It was a 230 by 300 column, I still remember. So will provide the circular dimension. We don't have a circle, it's 0. So if you see, if I change from circle, it gives us 0. If I change from rectangle, it gives us the area of the column. So now provide the unit weight of the concrete in this component. It's 24, which is okay, we're using 24. Then we also need to provide the average height of our columns, which if we look, it is definitely 3 meters. Yes, it is 3 meters. That is the average height. So it's going to be 3. Then it calculates the load for us. And then the stub column, whether it's rectangular or circular, let's go, it's rectangular. So section depth, this time it's 3 to this. Yes, we're good to go. Unit weight of concrete. What is the height of the stub column? So the stub column, if we look carefully, what we call the stub column is anything that goes below, just below the ground floor level. So to clearly visualize that, just say window. Okay, let me open something. Let's just go to structural layouts, tutorial layouts. Okay, there's no production drawing. Alright, so it's a different things. It's funny, I'm using a different, so I would already had this open. So when we look at our layout, so where we start measuring the stub from this, let me show you where we start measuring the stub. So the stub is measured from just there to the top of the base, and this dimension is, I cannot see what it is, so let me just, I don't know what is happening. Let me try to change the base plan. Alright, it's 1500. So 1500 is 1.5 meters, and the load we get is 2.48 kilonewtons. Once this is done, the next thing that I have to do is just go to the results. So this is where my results are automatically calculated for me, but then I have to remember to key in the number of components that this column or this building has. So it has one roof, so we're good. Then it has one first floor slab, which is carrying its loads to the foundation, as shown by this. This is the only slab that's monolithic with the structure which is carrying its load down to the foundations. And then the next thing is walls on slabs. I have 0. Then how many beams do I have? Since I already keyed in both the eaves beam and the first floor beams combined, so I'm going to have 1 set. Then walls on beams, I'm going to have 1 set as well. So number of columns, I'm going to have 2, because as you can see, we have a column on this level and a column on this level, a column all the way to the first and a column all the way to the eaves, so we have 2. And then number of stub columns, we have 1. So what it does, this is the result for the dead load, which is unaffected, and the result for the live load, which is unaffected. The total load is 487.12. Then these are the factors, whether you're using BS, sands, SABs, whatever you want to call it. In this case, we are not going to be using BS, we are going to be using sands. So in our case, the dead load factor, which is factored, is 369, and the live is 269, and the total is 638. And maximum allowable bearing pressure, which you get from your geotechnical investments, for this case we're using 750 kilopascals or 750 kilonewtons per square meter. So a preliminary sizing of our foundations, as we now go to Prokon, that's the required area under serviceability limit state. So you always size your bases using the serviceability limit state factor. So what you're going to do is you're going to say the force divided by the pressure, maximum allowable pressure. So the force divided by 750 is 0.6495 square meters. And then afterwards, assuming a square base each side, what you would do is just square root of that, and you'll find that you roughly need 900 by 900 reinforced concrete base. So yes, once you've done this, you've essentially just did the preliminary bases, did the load takedowns, and now you have an idea of what is happening and what you need to design. So this calculations, as you see, these are the calculations we are going to be using to design our foundations and to design our columns. So this is important. So this is why it is very important. So thank you very much for tuning in. This is where we're going to do it. So we've done for the middle column. We're going to do for all the rest of the columns, but I think I've already done them. Yes, I already did them. I'm quite sure I did. Yes, I did the takedowns for column 1, column 2, column 3, and column 4. Yes, because you don't really need to do it for the entire, you just need to do for the same columns, which most probably are just going to be the same. So thank you very much for tuning in. This is done, and yo, look at it, we now head into Prokon. This is about to get fun. Actually, it's about to get fun. Thank you, sorry about that. See you next time.